So it seems that we have everything set up in our chem.txt file, okay, in terms of our database file. Again, we will just double check the label when we actually go set it up so that we're referring to the correct kinetic block. Okay, so after we check our chem.txt file against our database file, we'll move on to setting up our initial condition file. And so these will include, again, setting the initial conditions for our aqueous species, our solid phases, and then all of our different reaction rate parameters. So again, I like to list them in that best practice order. So our aqueous species first, and then all of our solid phases next. Okay, and so our aqueous species will be specified in concentrations of moles per liter. Our solid phase, this first number is the volume fraction of this solid phase. Solid phase that's being degraded over the total amount of solid soil phase, and then our various reaction rate parameters, and we'll go through these one at a time to see what they all mean. So the first of our reaction rate parameters is our specific surface area, so that it represents this A value in our reaction rate equation. And so you'll set this for each of the zones. So this is the initial conditions for the precipitation coming into the system. This is the initial condition of the solid phase of the upper zone. It's labeled UZ in BioRT. It's the shallow soil zone. And then we also have the initial condition or the specific surface area of this organic carbon phase in the lower zone or the deeper groundwater zone. The next value we specify in our reaction rate parameters is the kinetic rate constant. So this is listed in the database, and if this is listed in the database, however, we do specify it in our initial condition files. The number listed in the database tends to be a more traditional literature value. However, when we do a lot of these modeling reactions, because so many of those kinetic rate constants that are determined are done in laboratory settings, they tend to not represent the kinetic rate constant that's actually seen in a natural system. So we've allowed the user to be able to specify this kinetic rate constant themselves. And so again, we have it for each zone here. And then the next parameter we will be able to amend is as Q10. This is part of this temperature sensitivity function. And so Q10 is the change in rate for a change in temperature. So we'll go over this again. Okay, yeah, Q10 represents the increase in reaction rate when the temperature increases by 10 degrees Celsius. So this is the reaction rate equation. So how much it will amend the reaction rate based on how much the temperature raises. So generally, we have a Q10 between 1.4 and 2.5. And so you can see how changing Q10 over different temperatures can change this soil, this temperature sensitivity. The next parameter we will look at is changing our soil moisture sensitivity parameters. And so this includes a soil moisture threshold value, as well as a soil moisture exponent. And we can go over those here now. So our soil moisture sensitivity function is kind of a piecewise function. I'm sure that's not the right word, but so we have a soil threshold value. And so this will be this threshold value here. From before the threshold value, we'll have an increasing relationship with soil moisture, and then after this threshold value we'll have a decreasing relationship. And so this can represent if you have too much soil moisture and you start having limited oxygen diffusion, this can actually inhibit reaction rates. So that's where we can start to kind of account for this oxygen limitation that may happen with saturation within our soil moisture sensitivity function. And then we also have this N exponent within our soil moisture sensitivity function, and this will really represent the sensitivity of the reaction rate to soil moisture. We can see by amending this N, we can change the shape of the curve and the shape of the response of the reaction rate to soil moisture. And then last but not least, we have our sensitivity function to water table depth. And so right now they're all going to just be set as 0 for simplicity. But yeah, so in terms of this water table depth to function, it's actually what we specify here is a product of this alpha and this n value. And so if n here is set as 1, it indicates decreasing reaction rate with a lower water table. And if this n is -1, it indicates an increasing reaction rate with lower water table. And then again, this alpha value is really just indicating the sensitivity of the reaction rate to the water table depth. And then the very last input file we will amend and set up are these numeric or precipitation chemistry input files. And so again, I like to make sure within this precipitation input file that I've listed all of my primary species. Again, in this precipitation input file, we will just include our primary species. I like to make sure that I have them in the same order I have specified them in my other input files. So pH, DOC, CO2, which is all of our aqueous species, and then our solid phase last. And so these will be all of the concentrations for each day that were observed in precipitation. Or if you're using the numerical experiment file, it'll be if you're trying to see what changes in precipitation chemistry could and how that could affect your system. Okay, so we will move on to part 2B of this video, which will be the next video showing how we actually input these into the input files and running, and then we'll look at some of the results.